Assalamualaikum warahmatullahi wabarakatuh. So, we meet again. So, this is still chapter 2, Rectifier, but the subtopic is the single phase uncontrolled half wave, where we are using the diode, and right now it is connected to what you call inductive load, where you can see here the resistor is connected in parallel in series with the inductor. So right now, as you can see from this diagram circuit, so our voltage V out is comprises of two components, which is our V out right now is VR plus VL. So the voltage drop across the resistor and also the voltage drop across the inductor. Okay, and based on the KVL also we can write down as this equation where Vs is equal to VR plus VL, and by using and then by converting into a time domain, so we can write down this one. So Vm sine omega t plus I omega t R plus L di over dt. Okay, so this need to be solved. So our objective is right now to get the equation for the current. So right now, since this is the inductive load is a non-linear load. So meaning that the current is no longer sinusoidal. So this can only be solved, okay, by using the first order differential equations. Okay. Okay, so I have redraw the circuit here. So we have a resistor, and you have your inductor here, and this is your Vs. Okay, so the current right now is a nonlinear current, which is I omega t, and based on the investigation that we have done by the previous researcher, so the current consisted of two components, which is the I natural plus I force. Okay, this one you can refer back to the circuit theory. So IN is the natural current due to the natural force, and IF, where is the current due to the force response. This one is a natural response due to the natural response, and IF is due to the force response. So what is natural response and force response? So natural response is when V source is set equal to 0. So we want to see what is the value of the current, and force response is actually where the diode is on and the voltage is available. Okay, so based on the simple KVL here, so we assume that the diode is on. So the IF here can be computed by using V over Z, right? I V over Z, so which is Vm sine omega t over Z. Sorry, this one should be in the polar form. So I in the polar form, IF is actually V with an angle of uh, with an angle of 0. So we assume that it's actually a reference, and impedance with an angle of theta. So we can find that IF is actually V minus theta over Z. And if we write down in terms of the time domain, okay, we can write down as a Vm sine omega t minus theta over Z. Okay, so this is our force response. While for the natural response is by setting the Vs is equal to 0. So by setting equal to 0, we can find that the I omega t multiplied with R, okay, is plus L di omega t over d omega t. This is must equal to 0, and this is the first order equation. So when we solve by using first order equations, we can finally obtain that I natural, I to the natural response is equal to a, which is a constant that we don't know, multiply with the exponential negative omega t over omega tau. Here, tau is the time, is a time constant where you can compute by using L over R. Okay, so right now, okay, sorry, this one. Okay, right now, our current, our nonlinear current, which is I natural, plus, sorry, I think we put I force first. I force plus I natural. Okay, so we write down the equation. So this one is a Vm over Z sine omega t minus theta plus A exponential negative omega t over omega tau. Okay, and we know that at when time is equal to 0, okay, the current is also 0. So by putting this relationship into this equation, okay, we can find that I at time of 0 is equal to 0. The value of the current is 0. Vm Z sine omega t is right now 0. So 0 minus theta plus A exponential 0. So meaning that is equal to 1. Okay, and then we write this one, we rewrite this, we will have our A, which is previously unknown. Right now we have already know the value. Vmz is actually negative Vmz sine negative sine theta. But negative sine theta, we can actually remove this, so we can finally Vmz sine theta. Okay, so we can finally write down our equation, complete current equation as Vm Z sine omega t minus theta plus Vm Z sine theta exponential negative omega t over omega tau. Okay, and this one is actually can be simplified further. Vm over Z, okay, sine omega t minus theta plus sine theta e exponential omega t over omega tau. Where Z is the impedance, where you can calculate by using this formula. Theta is your impedance angle, where you can also calculate by using negative tangent inverse omega L over R, and your tau is actually L over R. Okay, so this is the waveform that associate with the inductive load or single phase uncontrolled inductive load, where as you can see, this is the current, this is the voltage source, this is the voltage across the output terminal, and this is VR and VL. And I would like to note, to highlight that VR plus VL is equal to V out. And as you can see also here, the waveform of the voltage drop across the resistor is equal to the current out. And as you can see here is a what we call extinction angle. So this is the angle where the current of the circuits becomes zero. So you will be maybe you will notify that uh, the current is still flowing even though the voltage source becoming negative cycle. So this is the interesting part of the inductive load. Okay, using this circuit, I would like to explain why the waveform is like that. Okay, so please be noted that the load is non-linear load, so the current is no longer sinusoidal. Okay, so this is your Vs. During the positive cycle, the same operation will actually continue as okay, where as you can see, the diode is right now is forward bias, okay, meaning that the diode will turn on, and then this one, the current will flow to the resistor and inductor and flow back to the source. And I would like to remind you that the inductor here is also considered as an energy storage. So it will charging when the current is conducting, the inductor will actually store some energy from the circuit. Okay, and this is the current output waveform. It will start charging, okay, until at this particular time. This is pi, okay, and when the source become negative voltage, what happened? When the negative cycle, what happened? So when it is a negative cycle, the polarity of the source is changed, is inverted. So meaning that right now the cathode is positive and the anode is negative. So meaning that the diode will be in reverse bias. So reverse bias meaning that the diode is off. Okay, but you need to note that this cannot be happen instantaneously because of what? Because the energy stored, the inductor need to be released, okay, so right now as you can see, the energy has been stored in the previous cycle, in the positive cycle, but there is no way, there is no path for the energy to be discharged, okay, because right now the circuit is already open circuit. So what the inductor do is to force, is actually it will discharge the current and forcing the diode to turn on, okay, and then turn on until the energy stored inside the inductor is reducing to zero. So that's why we have here the current is like now is reducing to zero, and the time where the energy becomes zero is known as a extinction angle. So beta is actually what called extinction angle. There is a where the time where the current become zero. And this is repeated, okay? So this is your voltage. So your V out here, and you will have some portion here, negative portion here. Why? Because at this time, as you can see, at this time, where the current is still flowing, okay, the diode is on, and V out is connected to the V source. So that's why at the V out, we will have uh, uh, this negative portion of the voltage supply. Okay, so this negative portion will give effect to the voltage output, where the voltage output, the average voltage output, will become smaller or reduced from become reduced because we have a negative one.